Very pleased to introduce the talk tonight, which is going to be given by Linda Strubbe. Linda was born in New York, grew up in New York, and went to undergraduate at Caltech, graduate school at UC Berkeley, and is currently a postdoctoral fellow at the Canadian Institute for Theoretical Astrophysics, where she works on the tidal disruption of stars by black holes, which is something that you may not understand now, but hopefully you will by the end of the talk. And she's going to be talking about Snacktime for hungry black holes. And this is this public talk is associated with a conference that's going on here at Snowbird this week on black holes. That's it. If anyone is interested in future similar events, in attending similar events in the future, we have a sign-up list over. Raise your hand, Catherine. You can. She has a sign-up list, and if you're interested, you can sign up for future events there. Okay, so welcome, Linda.
Is it working?
Great. Okay. Great. Thank you guys all for coming tonight. Is this too loud? No. That's good. Okay. Great. It's really awesome to be here, and I'm really excited that all of you guys could make it out tonight, and that I could get to talk to you about one of the most awesome, amazing objects in the universe, and that's giant black holes. But before we talk about giant black holes, I wanted to start by talking about something that's much tamer and closer to home, but really beautiful, and that's comets. So I'm going to be asking you guys to raise your hands and stuff a lot tonight, and I hope you're okay with that and that your arms aren't going to get tired. Comets are giant, or well, not giant, they're small balls of ice and dust and dirt that come from far outside of the edges of our solar system in towards the Earth, and then we get to see them. Now, have any of you guys ever seen a comet? Can you raise your hand if you've seen a comet? Cool, it looks like a lot of you guys have. Can I ask anybody to tell me what it looked like? What did you see? Can we get a volunteer? Yeah, what did you see?
I saw a hail bob.
Yeah?
With the naked eye, and it looked just like
Yeah.
ditto. I saw Haley's as well, but it was convenient.
Anybody else want to tell me you saw a comet? Yeah?
I saw Aikute through a night vision goggles and it lit up the sky.
Oh, sweet. That sounds awesome. Well, is this, am I really not so loud? I can hear the feedback. No? Okay. Yeah, so I actually got to see my first comets when I had just gotten into astronomy for like a couple of years after I got into astronomy. So I first got interested in astronomy when I was in 6th grade. I was about 11. And me and my dad decided that we wanted to learn all the constellations of the northern sky together. So we went out basically every clear evening from in our backyard in New York, and we had a book out and a little red flashlight to learn the constellations and the names of the stars and stuff. And actually sometimes in the middle of the winter, we would get up in the middle of the night to see constellations that we otherwise weren't going to get to see for months in the future. My mom definitely thought that we were crazy, but occasionally she was nice enough to make us some hot chocolate and wait up for us in the kitchen. Anyways, a couple of years later than that, in 1996 and 1997, there were these two really amazing comets that I'm showing you pictures of here, Comet Hyakutake and Comet Hale-Bopp. And like you guys were saying, and probably others of you saw them too, they were amazing. They were bright enough that you could see them with your eyes for days, maybe even weeks if you were lucky, and you could just see their tail stretching across the sky. They were amazing. Did you guys know that there's actually a comet that's visible right now? Raise your hand if you knew that. Awesome. So there's a comet right now, and it's called Pan-STARRS, and it was actually brightest last week. Did any of you guys get to see it? More hand raising. Yeah, sweet. Some people did. I actually didn't. The night that would have been best for it last week in Toronto, there were really only like one clear night, and it was sick, so I was very disappointed I didn't get to see it. I think it's definitely still up right now, but I think you might need binoculars or a small telescope to be able to see it. But it's still worth trying to see it if you can. And so I'm mentioning all of these comets, and they actually have kind of funny names, don't they? There's Hyakutake, there's Hale-Bopp, and I was just talking about comet Pan-STARRS. And these comets actually get their names from the people that discovered them. So Comet Hyakutake was named after a Japanese amateur astronomer. Comet Hale-Bopp was named after 2 American amateur astronomers that independently discovered it, Hale and Bopp. And Comet Pan-STARRS, though, actually isn't named after a person because it was discovered by a team of people that were using a telescope called the Pan-STARRS telescope. So that's where it gets its name from. And I actually got to go and visit the Pan-STARRS telescope a couple of years ago. It's in Maui, Hawaii, and that was really awesome. So the Pan-STARRS telescope is a 2-meter telescope which has a really special camera that can it can take a picture in high detail of a large area of the sky really quickly. So it's actually covering large areas of the sky every night and taking a pretty good picture of a pretty big area of sky more than once a minute. And so that was how they were actually able to find the comet. So this is a picture showing you basically how they found the comet. So down here is the date, and you can see, I'll run it a couple of times, and you can see that this is just over the course of an hour. And what you're going to do is you're going to follow a little spot that goes along here, and that's the comet. All the other spots are stars, and they're just basically fixed in the background, but the comet's moving as it approaches us. In the solar system. There we go. You see it? There we go. I'll show you one more time in case you missed it. So there goes the spot, and that's the comet. So that's how Pan-STARRS found this comet. Pan-STARRS is this really neat telescope. It's actually doing a lot of different kinds of astronomy. It's looking for comets, but among the many other things that it's doing, it's looking for giant black holes that are eating stars. And so that's what I'm going to be talking to you basically about this evening. Probably a great place to get started is what actually is a black hole. We hear about black holes pretty often in the media, actually. There's like a Simpsons episode about black holes, there's songs about black holes. But the idea of a black hole actually goes back to the 1700s. Although the mathematics to understand how black holes actually work wasn't figured out until just under 100 years ago by Albert Einstein. But even then, the first black holes weren't discovered until the 1960s. And the term black hole wasn't coined until 1967. So the idea of black holes actually is fairly recent, even though we kind of hear about them every now and then in the news. So to actually understand in detail how a black hole works is really complicated because it uses Einstein's general theory of relativity. But although understanding in detail it's complicated, we can understand some really basic things about black holes without too much trouble. And so let's do that, starting with the idea of jumping. So let's say that, well, we're all here on the surface of the Earth, right? You guys are sitting in chairs, I'm standing, but suppose we wanted to leave the surface of the Earth and go into space. One basic first idea we might have, it's kind of silly, but maybe, what if we could just jump? So I'm going to hold on to the microphone and jump and hopefully it won't fall. So I'm going to jump and I'm going to try and go into space. Well, I didn't really actually get there. I made it a little way, but as soon as I got even a little way, I fell back down, right? What happened? Why didn't I make it into space? Anybody want to give me an answer? Gravity, exactly. So the Earth has gravity, and I jumped, but the Earth's gravity pulled back down on me right away. If I tried to jump a little harder, I might make it a little further into space. Let's give that a shot. Not quite. And that's kind of what I'm showing in this picture here. So if I jump a little bit, I go up, but I fall back. If I jump more, I go a little bit higher, but I still fall back. If you can imagine, I could have like a ball, and I could be really strong and throw it really hard, and it would go further, but it would still fall back again. So actually, if we want to go into space, we need to go really fast. That's why me jumping doesn't make it. That's why we need rockets. So if you want to actually make it into space, and you want to just jump and go, you need to go at 25,000 miles an hour. So that's more than 100 times faster than you could just go in your car horizontally. And I'm talking about trying to go vertically. So it's not that easy to leave the surface of the Earth. Now, let's think, that was leaving the surface of the Earth. Earth? What if we thought about leaving the surface of the moon instead? We could, again, try and jump and see how far we get. And the question that I want us to think about for a second is, if you jump on the surface of the moon, rather than the surface of the Earth, what'll be different? Will you be able to get higher, or will you go lower, or will you just get to the same height? Maybe many of you guys know the answer already, but I want you to think about it for a second, and maybe chat with your neighbor and make sure you guys agree. And I'm going to give you a second, and then I'm going to ask you guys to raise your hands to tell me the answer, okay? So let's have a little quick chat on it.
Yes, there is.
Have we figured it out? Okay, I see lots of discussion happening, so this is good. What I want us to do is figure out your answer. If you want higher, raise one finger. If you think it's lower, 2 fingers. And if you think it's the same height, 3 fingers. And on the count of 3, I'm going to ask you to raise them all at the same time. You don't have to participate, but it would be really fun if you did, okay? All right, 1, 2, 3. Let's see. Good. Okay, thank you guys all for raising your hands. And I saw a lot of 1s, and that's awesome because that's the right answer. So, if you jumped on the surface of the Earth, you would get higher. And you've probably seen videos of astronauts walking on the moon, and they're like going around like this, because they can jump higher. And the reason is that the moon is less massive than the Earth. And so it has less gravity, and so that means it's easier to escape from it. Dear. Keenan, quite unexpected.
That was not a good idea.
Maybe we won't bother with that.
Yeah,
I can just
okay.
go over and keep
I'm happy to.
Okay, can you? Yeah, but we have to make sure we're fast there with Sorry. Okay, great. So, if you jump on the surface of the Earth, you reach higher. And that's because the moon's less massive, and so it has less gravity, and so it's easier to escape from its surface. So to escape from the Earth's gravity, we said you need 25,000 miles an hour, but to leave the surface of the moon, it's not as hard. You need only 5,000 miles an hour. Probably still not going to manage to pull that off with your car, but at least it's a little easier than it is to leave the surface of the Earth. And so what we're learning from this is that more massive or more dense objects have more gravity, and so they need a larger speed. You need a larger speed to escape from them. So now what I want us to do is imagine something kind of crazy. What if we could imagine an object that was so massive or so dense that its gravity was so strong that jumping couldn't let you escape, rockets couldn't, and even rockets couldn't let you escape? Can you guys think of anything that's faster than a rocket? Raise your hand. It's an idea. Yeah. Light. Great. I was prepared for other answers in between, but we'll go straight for it. So yeah, so light goes faster than a rocket. Now we can actually imagine something that even light couldn't escape from. Next slide. Next slide. So you guys probably know that although light goes really, really fast, it actually has a speed limit, which is about 1 billion miles an hour. So that's really, really, really fast. But it's still a maximum speed that light can go. And so we can imagine something that's so massive that even light can't escape from it. What's something that goes even faster than light? Any ideas? Yes. Any other ideas? That was a boring answer.
Tachyons?
Which?
Tachyons?
Tachyons, great. Yep, if you can find some tachyons, we will put them into play. Cool, okay, so yeah, so the answer is nothing. We don't know of anything that can go faster than the speed of light. And so if even light can't escape, then that means that nothing can escape. And that's the object that we call a black hole. So what the idea is that if you can imagine an object like that, once light can't escape from it, that means that the gravity is so strong that it pulls all the mass to the center. it goes from being a bigger object and collapses into a point of infinite density in the center. So here's kind of the picture of it as the anatomy of a black hole. So out around the black hole is a place that's called the event horizon. And that's the place where even light can't escape from it. So if you're inside there, you can fire your jetpack rockets as fast as you want, and you're still not going to be able to escape. But actually, if you were falling into the black hole, you would pass through that possibly without experiencing anything, because it's not actually a solid surface. You'd fall all the way into the center where there's the point. But so that's a great question that we can figure out in our heads. What actually happens if you fall into a black hole? Nothing special actually happens in the event horizon, but it's gonna hurt, unfortunately. So for the sake of science and for all of you guys, I'm gonna put myself out there as a test subject. This is a picture of me skiing in Canada a couple of weeks ago, and I'm gonna put myself fairly close to a black hole, and we're gonna see what happens. So there I am. The problem is that the black hole's gravity is stronger when you're closer to it. And so it's stronger at my feet than it is at my head. And so what that means is that the black hole's gravity is going to pull me apart. So the closer I fall, the more difference the black hole's gravity is between my feet and my head. And so as I go into the black hole, I get super stretched out, and it's going to be pretty painful. And as I keep falling and falling, eventually I'm going to get to the center of the black hole, which is the singularity. So that's the point at the center where all of the mass is concentrated. And this is an infinitely dense point, so we're taking an amount of mass and squeezing it into infinitely tiny volumes. This is crazy, right? This is pretty outrageous. And you can kind of understand why Albert Einstein, when he came up with his equations of relativity, didn't even believe that black holes would probably actually exist. But astronomers have been working hard, and now we know pretty well that almost all galaxies have black holes, and not only do they have black holes, but each galaxy has one giant black hole living at its center. Seems crazy, but it turns out to actually be true. So to understand how that works, I'd like you guys to all think about whether you've ever seen the Milky Way galaxy, which is the galaxy that we live in. Can you raise your hand if you've ever seen the Milky Way? Great, looks like almost everyone has. Here in Utah, you guys have absolutely beautiful skies. So I would hope that many of you guys have managed to go somewhere that it's dark enough that you can see the Milky Way. And I'm actually showing a picture here. I didn't take it, but it's of the Milky Way seen from Bryce Canyon, which isn't that far from here. I went to Bryce Canyon with my brother several years ago, and after a great day of hiking around in the hoodoos and stuff, we went back to the parking lot, which was totally deserted, and we got in our warm sleeping bags because it was November, so it was pretty chilly. And we just lay there on the ground looking at the sky for literally an hour, like not moving, just looking at the amazing stars, and we could see the Milky Way, and it was gorgeous. So, as many of you guys will have seen then, the Milky Way is this band of light that we see across the sky at certain times of year. And that is telling us that we actually live in a galaxy that we call the Milky Way. That's how we know it. So our Milky Way galaxy is basically shaped like a frisbee. So I'm an ultimate frisbee player, so that's the. So it's a disc shape. And if we look kind of along the sides of the frisbee, then we're going to see extra brightness from all the stars that are there. And so that's the band of light that we see in the sky. This isn't actually a picture of our Milky Way galaxy, because if we were going to take a picture like that, we'd have to go outside the galaxy, and we're not going to be able to do that anytime soon. So this is based on data and Earth's impression put together. This is kind of. So we live in the Milky Way galaxy, but the universe is actually filled with lots of different galaxies. There are tons and tons and tons of galaxies out there, and each one of those, or almost each one of them, seems to have a giant black hole at its center. So let's think about the giant black hole that lives in the center of our galaxy. So I wonder if you guys have seen the constellation Sagittarius at any point, or at least have heard of it. Sagittarius? Whose zodiac sign is Sagittarius? Gotta have at least. Okay, so Sagittarius is a constellation that we can see from around here in the southern sky in the summertime. And Sagittarius is the archer, but there's actually another way that we can connect the points of the constellation Sagittarius. Instead of getting an archer, we get something sort of similar, which is the teapot. And so that's what I'm showing you here. So you can see kind of here's the handle to the teapot. This is the lid, and here's the spout. And what's really cool is if you follow these two stars in the spout, you get to a spot over here, which is marked with an X. Now, if you went outside and you actually looked at that, you wouldn't see anything special at the location of the X. It is in the band that's the Milky Way, which you can kind of see, but there's not any nice little X telling us there's something special there. But there is something special there, because that's the direction to the center of our galaxy. And if you followed that direction for 24,000 light years, you would end up in a giant black hole that is as massive as 4 million of our suns, all packed into one tiny little point. It's crazy. And like I said, we think that basically all galaxies have a giant black hole like that in their center. And so, next. And so the next question that you ought to ask is, I'm telling you some kind of outrageous things. How do we actually know that giant black holes are out there? And that's how science works. You shouldn't just believe me because I tell you. You should ask, how do we know? The way science works is we have ideas, we observe the world around us, we try and come up with ideas about how it works, then we make predictions, and we try and go out and test them, or make new observations of the world around us and see whether they line up with the ideas that we had. And in that way, learn more and more about how the universe actually works. So I'm telling you that we think that all galaxies have a giant black hole in the center because we actually have some observational evidence to tell us that. Unfortunately, it's not that easy to find giant black holes, right? If we just had the darkness of space and we put ourselves a giant black hole out there, it would just look like blackness. So we need some other tricks up our sleeve in order to be able to find giant black holes. And one of the clearest ways, is watching stars move around the giant black hole. So to understand how that works, first we're going to think about how we can tell that the sun is there in the solar system. So this is just a schematic drawing of the solar system. As you know, in the solar system we've got the sun, and we've got all these planets that are going around the sun. We've also got some comets that are on kind of crazier orbits, just to make sure that we can all see them. This is like a comet orbit going in like this. Here's the orbit of Mercury, say. This is the orbit of Jupiter. And by looking at the planets going around the sun, we can actually tell that the sun was there even if we couldn't see it, right? And we can actually even tell the sun's mass from that by looking at how fast they're going around. And so we can pull the same trick with the giant black hole in the center of our galaxy, except instead of planets, we're going to have stars going around it. So let's see what happens. If we replaced our sun, this is just kind of an aside before we go to the giant black hole in the center of our galaxy, but what if we replaced our sun in the solar system with a black hole that was just the same mass as our sun, but it's a black hole instead? What do you guys think would happen? Any ideas?
Very dark.
It would be very dark. That's definitely true. What do you think? Yes?
Wobble.
Yeah, we might get a little bit of precession. But the main thing that's going to happen is that's right. All the planets are just going to keep going around the black hole the same as they did before. A lot of times we have this idea that black holes are just like cosmic vacuum cleaners, and if there's a black hole there, then anything nearby is just going to get sucked on in. But that's not actually true unless you're really close to the black hole. And so if we replace the sun today with a black hole that was the same mass, all the planets would just keep orbiting around it, but it would be dark and cold. So with that idea, let's go to the giant black hole in the center of our galaxy. So in this picture of the solar system, we're replacing the sun with a black hole, and we're replacing all the planets with stars. And now we're going to tell that the black hole is there from watching stars move. I'll actually control that for a second. So what I'm showing you here is actual data from the center of our galaxy. This was taken by the Keck telescope in Hawaii from a team of scientists at UCLA in California. And each of these colored spots represents a star. The little numbers near them are the names of the stars. They're not very interesting names. And what we're going to see is that the stars are going around some unseen objects. So like in the solar system, it would have been the sun, but here's going to be the giant black hole. And so I'm going to play you the video, and what I want you to do is see if you can figure out where the giant black hole is that we can't see. And I've put 3 numbers for you, number 1, number 2, and number 3. And when we watch the video, we'll play it a couple of times, I'm going to ask you guys where you think the black hole is hiding. Okay? So here we go. There go the stars. Let's watch it once again. Remember, we're trying to figure out whether the black hole is at point 1, point 2, or point 3. All right, having seen that, I now would like to ask you guys where you think the giant black hole is. So if you think it's 1, I'm going to ask for 1 finger. If you think it's in position 2, I'm going to ask for 2 fingers. And if you think it's in position 3, I'm going to ask for 3 fingers. Okay? Ready? Set. Let's go. Cool. Okay, I think I see everybody with 2 fingers raised. Maybe not. That's right. The black hole is at the center of the picture, which is kind of a cheating way that you could tell. Well, let's watch it again. And now we've replaced the black hole with a star, just a symbol, and you can see all these stars going around the black hole. In particular, let's watch this one right here. It's called SO2, and it's going to go on this yellow orbit. So as I said, these orbits don't look like orbits in the solar system that are going in nice little circles. They're actually more like the orbits of comets. So when we looked at the picture of the solar system before, we saw some of the orbits were these big ovals. And so that yellow orbit, that's a big oval too. Let's watch it once more. This video is so awesome. So here goes the star SO2. It's coming towards the black hole, speeds up because the black hole's gravity is so strong, and then it goes off away again. And so from all of from data like that, and as you actually I didn't even mention it, in the top left-hand corner was the year. So this data was, I think, started in 1995 is the data that I'm showing you here with this video. So they've been working hard for a long time to get all of this data on the center of our galaxy. But this is really pretty compelling evidence that there's a giant black hole in the center of our galaxy. And by using similar techniques, we can tell that there are giant black holes in a lot of our neighbor galaxies too. And so the next question that we should definitely ask ourselves is how do giant black holes become giant? Where do these giant black holes ever come from? It's crazy. Or another way that we can ask the question is, what do giant black holes like to eat? Yeah, giant black holes like to eat lots of different things. I'm going to focus on a couple of them, but next. So the simple picture for how a giant black hole becomes giant is it starts out small, then it eats things, and then eventually it becomes giant. Kind of like people. So first we need to start by creating some little black holes. And part 1 is basically when we think that when a big star dies, it explodes, and that leaves behind a little black hole. So this explosion you guys might have heard of before. It's called the supernova explosion, and these are super bright. Only big stars do it, so you don't have to worry that our sun is going to explode and leave behind a black hole. But pretty big stars, when they get to the end of their lives, they explode and they leave behind a little black hole. And then over time, small black holes grow by eating stuff. And they like to eat lots of different things. But mostly they like to eat gas. That's kind of their dinner. On the side, they can sometimes eat other black holes. Someone said planets. Sure, they eat planets. And occasionally they eat stars. That's kind of their like little tasty snack. And so they start out small, and then they grow a bit, and then next, and then they get bigger, and then they grow some more, and then if they get to eat enough stuff, then they can eventually become giant. But how do we know that that's true? Where does this idea come from? How do we know? That's one of the main questions we should be asking throughout in science. How do we know? Next. And so in order to understand how we know, the way that we know is we see evidence that this is actually going on. And so to understand how that works, I'm going to take us out of the black hole picture for a minute, and we're going to do a little experiment. It's totally different. So it's kind of cold out. I don't know, many of you guys maybe went skiing today, or at least you were like out and about in town. It's kind of cold out. So maybe when you came inside, you rubbed your hands up a little bit to warm them up, right? This kind of warms your hands up. I'd like everybody to take your hands out. And let's rub your hands together. So the question is, if you rub them slowly or faster, or slower, or faster, which one makes them hotter? That's the question. You can have a little quick chat with each other, make sure you agree. You can have some more hand rubbing, just to be sure. Okay, and so now I'm going to ask you guys for your answers. 1 finger if you think it's slower, and 2 fingers if you think it's faster. Ready? Set, go. Everybody, all at once, come on. Great, okay, I see twos out there. So good, you guys are good at rubbing your hands together. That's right. If you rub them faster, then they get warmer. So let's remember that because we're going to need that in a minute when we have gas feeding the black hole. So galaxies are full of gas. Maybe you guys have seen a picture like this before. Astronomers love showing beautiful pictures like this because they're so beautiful. This is a nebula called the Rosette Nebula that's right here in our galaxy. And you can see there's lots of things going on. We've got these bright stars in the center. We've got these dark patches of dust. And they're different colors. There's like blue and red, which corresponds to different chemicals that are there, and also to different mechanisms for producing photons, which is how we actually get to see stuff, so different colors. Next. So galaxies are filled with gas like this, and over time, through different ways, gas can flow to the center of the galaxy. We're going to see that one of the main ways is when two galaxies crash into each other. We'll see that more in a minute. So over time, gas that fills galaxies flows to the center, yes. And as the gas flows to the center, it speeds up. So as it spirals in, it's kind of like water going down the drain. So if you think about the last time you took a bath, and then you let the water all go out, as the water gets closer and closer to the drain, it spirals and it speeds up and up and up. And the same thing happens when gas flows into the center of the galaxy and is about to go into the black hole. Next. Now, as we know, when things move fast, they heat up by rubbing, by friction, right? So just as my hands got hot when I rubbed them like this, imagine if you had gas going super, super fast, just as it's about to go into a black hole, it gets incredibly hot. And as you guys know, though you might not realize that you know it, hot things glow brightly. So if you think about in your kitchen, this is maybe you have a range stove at home, or maybe you have a toaster oven or something. These things glow because they're hot. So if we turned off the light at home in the kitchen, you wouldn't be able to see like your fridge or the cabinet, but you'd still be able to see the glow from the heating element on your stove, and that's because it's hot. And the same thing happens when gas is falling into the black hole. Next. So we've got this super hot gas that was spiraling in, it heated up by friction, and then it glows really brightly just as it's about to fall into the black hole. Unfortunately, the galaxies are so far away that we could never see this kind of detail. Well, maybe not never, but it's going to be really tough to see this kind of detail. And so instead what we get to see, next, is just a bright glow where there's a galaxy, an incredibly bright glow. And the way that we know that there's a giant black hole there is we can't think of any other way that could produce such an incredibly bright glow. So we conclude when we see a really, really bright glow like this, that there's a giant black hole there and that it's eating really fast and growing. These bright, fast-growing giant black holes are called quasars, and we get them when two galaxies crash into each other. So remember, galaxies are filled with gas, and when they crash into each other, a lot of the gas gets sort of thrown in all directions, and much of it can end up flowing to the center of the newly merged galaxy and feed that giant black hole in the center. And the giant black hole kind of gets to have a feast and grow to be even more giant. And so this is the way that we think that giant black hole, this is where most of giant black holes do their eating. So they might like to eat other things occasionally, but their mainstay, their dinner, is the gas that they get to eat when two galaxies crash into each other. Unfortunately, or maybe fortunately because it's interesting, there are a lot of details of how that gas flowing in and feeding the black hole that we don't really understand. And there are two particular complications that aren't that difficult to understand that I'm going to try and explain to you. The two things are heat and magnetic fields. So let's think for a second about if you have like a hot cup of coffee, or maybe you've got some water on the stove or something, and you see steam rising off of it, right? So just like me, when I jumped up into the sky, or the slight amount of air here, I got pulled back down again by gravity. And the steam from the stove is also feeling gravity from the earth, but instead it manages to rise, and that's because it's hot. And we saw the gas that falls in and feeds a black hole heats up a lot. And so just like steam, we might think that actually some of the gas might heat up and flow away from the black hole instead of falling in and feeding it. An additional complication is magnetic fields. So have you guys ever played with a magnet and some iron filings? Hands up. A lot of you guys have. If you haven't, you should. It's pretty fun. So if you have a magnet and some iron filings, if you move the magnet around, the iron filings move around too, because they're being pushed by the magnetic field. And so something similar happens with gas that's falling in and feeding a black hole. The strong magnetic fields can grow in that gas, and then other bits of gas kind of act like the iron filings. And so, although the gas is trying to fall in and feed the black hole and help it to grow, like iron filings, bits of gas get pushed away. And so heat and magnetic fields push gas around and can keep the black hole from growing at the rate that we might have thought it would. So there's lots of things, but there's lots of details about how this actually works that we don't really understand. So one place that we can go to learn more about how this actually works is, instead of focusing on these feasting times of black holes when they're eating lots of gas from a galaxy, but thinking about the occasional tasty snacks that black holes get to eat, which is these little stars. So let's study black holes snacking on stars, Pac-Man style. So the idea is that stars orbiting the black hole occasionally wander too close to it. So we already watched this movie of data of stars going around the giant black hole in the center of our galaxy. And although the giant black hole has a lot of gravity, the different stars, they also have gravity, and so they're pushing, or they're tugging on each other's orbits. And occasionally, a star that was going on a perfectly safe orbit around the black hole will get pulled on by another star, so that now, instead of going safely around the black hole, it's going on an orbit that's going to take it really close to the black hole. So it could start out far away over there and get closer and closer, and eventually it gets so close to the black hole that it actually gets ripped apart. And the way the star gets ripped apart is similar to how I, on my skis, got ripped apart when I was falling into the black hole. So remember that the gravity of a black hole is stronger when you're closer to it. And so if you think about a star, I don't think we'll be able to reach, the side of the star that's closer to the black hole is going to feel more gravity than the side of the star that's farther from the black hole. And so just like I got stretched out, the star will, just as I got stretched out, the star gets stretched out as it goes towards the black hole. And so it stops actually being a star, but goes back to being gas, just gas. That's what stars are made of, that's what the sun's made of. It goes back to being gas. And just as we know that gas heats up, and so gas falls in and feeds the black hole, similar to how it works in quasars, and we'll see what differences are in a second. I wanted to show you a simulation that a graduate student in California named James Guichon did, showing you what we think might happen with the gas that used to make up the star as it falls towards the black hole. So I'm going to show you the calculation again in a second. Realize that this is a calculation. This isn't a movie of actual data that's been taken. But so the black hole is up there, and you're going to have a hard time seeing it, but there's going to be a little dot that comes in towards the black hole, and that's going to be the star, and then the star is going to get ripped apart by the black hole's gravity, and then bits of gas are going to end up flying in all directions. So there goes the little star, and it got ripped up. And so now all that orange stuff is the gas that used to be the star. So it's not a star anymore, it's just all of this gas. And so gas that used to be part of the star falls into the black hole. And just as it did for quasars, that gas becomes super hot and it glows brightly. But instead of glowing brightly for millions of years like it might in a quasar, in this case it glows only brightly for weeks, because there wasn't that much mass in the star, and pretty soon the black hole's just eaten its entire tasty, starry snack. Next. So the galaxy, just as for quasars, the galaxy is too far away to actually see in detail the gas as it falls into the black hole. But what we can see is the center of a galaxy become much brighter for weeks, kind of like a mini short-term quasar. And the reason that we would want to take a look at this is that starry snacks have various things that they can teach us about giant black holes and how they grow. So first of all, if we actually see a galaxy, that brightens like this in the middle, then we know that a giant black hole lives there. Second, we also can study the light that we observe from the black hole eating a star to learn about how gas flows into giant black holes to make them grow. So we'd love to go off and search for black holes eating stars and use them to help us understand how black holes grow and find new black holes. Unfortunately, it's a pretty challenging thing to do, and that's because these events are both rare and quick. So a giant black hole probably eats a star only every 100,000 years or so. So if we were like, great, we know that our giant black hole in our center of our galaxy is going to eat a star, we'll just sit there and watch. We'd have to wait for 100,000 years. So probably we're not going to be alive anymore at that point. So a better plan is to monitor a whole bunch of galaxies. If we can monitor many, many galaxies, then eventually the probability that we actually get to see a giant black hole eating a star gets reasonably high. But not only do we need to monitor lots of galaxies, we need to keep looking back at them every few days, because remember, it turns on, you see this mini quasar, and then it turns off again in just a matter of weeks. And so if you're not looking all the time, you're going to miss it. So you need a very special kind of telescope survey in order to be able to find this. So the first discoveries of giant black holes eating stars were made by the Rosette X-ray satellite, which found several possible black holes eating stars in the late 90s. And these were really important observations. But they're difficult to interpret because the technology wasn't good enough for us to get lots of data about any of those events. Next. But now, today, we're starting to have these new special telescope surveys that allow us to get much better data on these black holes eating star events. So 3 telescope surveys that are doing this are the Palomar Telescope in Southern California, the Swift satellite, which is an X-ray satellite, so that's actually in space orbiting around the Earth. And then, of course, where we started off this whole conversation with the Pan-STARRS telescope in Maui, Hawaii. And each of these telescopes has actually found a giant black hole that we think is eating a star. In fact, the Swift satellite has found 2. Next. And so we can take a look and see what are we actually learning from discoveries of black holes eating stars. And one thing that we're finding is not so giant black holes are actually doing some of the eating of stars. And that's really interesting because that's a step along the way from small black hole on its way up to giant black hole. So we can learn a lot about how black holes go from being small to giant, and we can actually catch them in the act along the way. And secondly, we can learn about heat and magnetic fields pushing the gas around as it tries to fall into the black hole. And it looks like, indeed, they do push gas around, and we're trying to learn more about how that actually works. Next. So 2 of the telescopes that I just mentioned, Pan-STARRS and Palomar, are undergoing big telescope upgrades soon. And then in the next decade, we're looking forward to a really powerful telescope called the Large Synoptic Survey Telescope, which is going to be built in northern Chile. And this telescope is powerful enough that it could find hundreds of giant black holes eating stars every year. So this would be really exciting for our studies of how giant black holes grow to be giant. So I hope you'll stay tuned in the news because you might get to hear about these current telescope surveys, and then in the future, this telescope survey finding giant black holes eating stars. So that's basically the story of giant black holes eating stars. And so to conclude and summarize, I'd like to take us back to the beginning and remind us that we're talking about these crazy objects called black holes. They're objects that are so massive or so dense that gravity is so strong that light even can't escape from them. And as crazy as it seems, basically most galaxies have a giant black hole living at the center of the galaxy, ours included. And giant black holes like to eat nearby stars, which gives us a way of learning about how giant black holes grow from being small all the way up to being giant. And so I hope you guys will think more about this in the future. The next time you rub your hands, or the next time you're jumping to try and escape from the Earth, or the next time you're looking at the heating element on your stove, all of that simple physics, although physics can get complicated fast, it's based on a lot of simple things that you guys see every day. And I really hope that sometimes you'll go outside and look at the sky, check out the Milky Way galaxy, check out all the stars. They're incredibly beautiful, and you can remember that as crazy as it seems, in the constellation Sagittarius, 24,000 light years away, our Milky Way galaxy has a giant black hole, and so do almost every other galaxy that we know. Thanks very much. I would love to answer your questions. So if you have questions, let me hear them. Yeah.
You said that the center of a black hole.
To me, why isn't the amount of mass that's in there infinite? So it's taking a normal amount of mass, like the mass of a star or even a million stars, but it's compressing that all into one point. But you don't have an infinite amount of mass that you're starting from. It's just that you're taking that sort of normal finite amount of mass and squeezing it into a volume that's incredibly small. So the density is infinite, the amount of mass there.
Galaxies collide. Does one black hole, or do they ever kind of balance out and sort of?
Yeah, great question. So they probably dance for a while, but ultimately manage to merge into one. So you have both galaxies as the galaxies come in, each of their giant black holes kind of falls to the center, and they go around each other in circles for a while. A kind of friction with the stars causes their orbits to get smaller and smaller, and at the end, actually, a phenomenon called gravitational waves that you may not have causes them to go all the way in together. So that's kind of waves in space-time. It's really kind of crazy. It takes energy away and causes the black holes to come all the way in and become one ultimately at the center. So we see quasars as we have the giant black holes falling into the center, and then the gas that was coming with them. So that forms a quasar.
Layman's perspective, ski bum,
Nice.
with little math background. What's the difference between a black hole and dark matter? And are they one of the same, but or do we not even know?
Yeah, that's an excellent question. And astronomers give these things really confusing names so that they sound like they should probably be. But actually, black holes and dark matter are pretty different. So black holes can be made of just normal everyday matter, like from the table or from a star or from the Earth or from you. Whereas dark matter is something really different. So dark matter is so back to black holes. Black holes are dark because they're so dense the light can't escape from them. That's a black hole. But dark matter, even if it wasn't particularly dense, if we had dark matter in the shape of a table right here, we wouldn't be able to see it. So dark matter just has these weird properties that it doesn't interact with light, essentially. And we think that most of the universe, most of the mass of the universe, is this dark matter. And we can infer that it's there by its gravity. So that's similar to how black holes work. In both cases, you can't see them, and you have to use things orbiting around them in order to tell that they're there. So that's what we do in the presence of dark matter too.
So are there other black holes like we see in our galaxy besides?
Yeah, absolutely. So our galaxy has a whole bunch of these small black holes that I mentioned, for sure, millions of them. Yeah. So every time a big star ends its life and explodes as a supernova, it leaves behind a small black hole, or at least many times that it does. It leaves behind a small black hole. And most of the time, those black holes will just wander around in the galaxy. Occasionally, we can tell that they're there because there's something else orbiting around it. And so we can either tell by watching that move around it or by feeding it, the same way as we can tell the giant black holes are there by them feeding. But yeah, we think that, we have lots of evidence to show that there are lots of small black holes in our galaxy and in other galaxies as well. And there could also be some black holes kind of in intermediate mass in between those. So there's the small ones and there's the giant ones, and maybe there's some ones in the middle, and we don't really know. that's a really good question. It seems like it would be, but it's actually not. So the mass of the black hole, in the giant black hole in the center of our galaxy is like 4 million suns, which is a lot, but the mass of our galaxy is something like 10 billion suns, or even 100 billion suns. And so the gravity of the black hole actually is only important for its kind of nearest neighbors. So the movie I showed you with the little stars going around the black hole, they definitely are held there by the gravity of the black hole. But stars further out, they care more about the mass just of other stars that are around. And so if we got rid of the black hole in the center of our galaxy, like our orbit as the solar system going around the center of our galaxy, we wouldn't care. The giant black hole's gravity just isn't important enough. There could, yeah, especially at the point when two galaxies have just crashed into each other. There'll be a while where you have two black holes and they're both doing this dance. We're here. Yeah, they could. That's sort of an active area of research. We don't really know how these giant black holes really get all the way to the center. And there are galaxies where we can see clearly that there are two giant black holes. So basically, when I was talking about quasars, we can see galaxies that basically have two quasars in them. And we interpret that to mean that there are two giant black holes there. We don't know how long that lasts. We think that probably eventually the two black holes do come all the way into the center and merge into one, but we don't really know how long that takes, and maybe there are systems where it never happens. Yeah. Is there a limit to how big a black hole can be? No, I don't think that there is. The largest black holes that we know of are about 10 billion suns. So that's incredibly huge. Remember, our black hole is 4 million suns, and I'm talking 10 billion suns. But that's just because that's the biggest black holes that we've found. And there's nothing to say that you couldn't have a larger black hole if you could form it, if you could feed it enough gas and stars and other black holes and things. It could in principle grow to be as big as you want. Yeah. Earth's orbit would not speed up. Earth's orbit would actually be unaffected. It seems kind of weird, but actually the gravity of a black hole is only strange right pretty close to the black hole. So if you were right by the black hole, you would totally get sucked in, yes. The Earth's orbit would speed up and then it would fall all the way in and we'd be done. But we're far enough away from the sun that if you replace the sun with a black hole, we just feel the gravity of the black hole, and we feel the gravity of the sun, and it would just be the same. So we'd keep going on our nice little circular orbit. Yes?
Is it true that scientists have produced
I think the answer is no. If they did, it would be incredibly tiny, and we wouldn't notice or care. But I can't actually give you a really awesome answer about that, but we're going to be fine. Is there a question back there?
Oh,
Yeah.
So, my question, I actually have two for you.
Okay.
You're standing up very high, so it's a question. Energy. So, if scientists begun to raise the possibility that it is theoretically possible to harness that energy.
Good question. So it isn't actually totally true that energy can't be destroyed. It's true that mass and energy can't be destroyed. So mass can turn energy, and energy can turn into energy, and energy can turn into mass. And when you have gas falling into a black hole, although that mass is something that we can't get out again, it's still there. It didn't get destroyed. There is a question about information and whether information can be destroyed. And that's a topic of current scientific research.
How does that relate to the whole theory of
I'm not sure.
from Brian Greene's perspective?
For what?
From Brian Greene.
Brian Greene's perspective. I'm not a total expert in this direction, so I'm not totally sure. But what was I going to say? But I do know that there is a question about when matter falls into a black hole, whether any information that it carried is destroyed or not, and if somehow there would be some way of getting that information back out again. Yeah, it's pretty crazy stuff.
You make more sense than Brian Green does.
Thank you.
I had a question in reference to the graphic you had. You can have a predictable size for an event horizon based on the actual singularity. Is that?
Yeah, so that's definitely an area of active research. We don't really know. So I've been talking about Einstein's theory of general relativity, but we don't think that general relativity applies when you get to really, really tiny scales. So you've probably also heard about theories of quantum mechanics, and those apply when things are really small. But we don't have a theory that puts those two theories together and makes them both make sense at the same time. And so that's what you would need in order to be able to answer the question, what's the size of the singularity? So as yet, we don't know.
Yeah, I was wondering if that picture was like an accurate representation.
No. I meant to depict the singularity basically as a tiny speck, infinitely small, but it maybe has some finite size, depending on we really don't know right now. Yeah.
Your other graphic. Have there been planets discovered around black?
Good questions. Questions about whether there are planets around black holes. It would be, I'll start by just answering observationally. It would be really hard to see a planet around a black hole. Stars shine, planets don't. However, there certainly could be planets around a giant black hole. There's nothing to say that they wouldn't get to exist there. And in fact, they could hold themselves together longer than a star could before getting ripped apart. So they could maybe exist closer into the black hole. How you'd actually form a planet right in close to a black hole is a good question. Those stars that we know that are around black holes, if they formed sort of normally, they could potentially have planets around them just the same way that the solar system does. So there could be planets around the black hole that way. I'll add one more layer of complication, which is that as the star gets close to the black hole's gravity could pull the planet away from the star. So just like, as I'm falling towards the black hole, my feet get pulled on, the same way the planet would get pulled away from the star. And so that could be a way that we would have planets just wandering around the black hole. Go on.
Just about the nature of studying black holes. Observational, meaning it would have to be light traveling between. And if the nature of a black hole is that past a certain point, light doesn't escape. There's really only so much you can observe. It has to escape so you can observe it.
Yeah, that's completely true. So how do we actually study what's going on inside black holes? We have to do our best theoretically. At the moment, there aren't really observations that we can do to test our theories of what goes on inside black holes. We can study what goes on right up until the edge, but not once it's inside. But at the moment, we don't even have a theory that explains what's going on inside the black hole that we could want to test. I mean, there are ideas, but we don't have anything that even. Thanks for coming, everyone.
So dark energy. So now they say from Einstein's deduction of the cosmological constant is probably but what he predicted was that the cosmological constant predict the universe that was